Yes. So, we'll set up from the current slide, and as soon as it comes up, there we go. All right, we're in Chapter 4. The title of Chapter 4 is Vector Spaces. And we're in Section 4.2, and the title of Section 4.2 is Vector Spaces. Okay, so this must be the key section in Chapter 4, since the section name is the same as the chapter name. Okay, vector spaces. We gave the definition of vector spaces earlier. I believe we're starting on example 1. Is that right? Okay. So, we've now got our projection, so I can quit talking and start writing. Now, when I say R2, not followed by D2, okay, what are we talking about? Second? It's a plane. Just plain R2. Plain R2, yeah. It's two-dimensional space, which would be a plane, okay? Doesn't have to be the XY plane. It could be the YZ or XZ or just any old plane, but that's R2, two-dimensional space, okay? That two-dimensional space with our standard operations, and I hope you remember what that is, but we'll go over that, what those are. It is a vector space. This is this example. So basically one way you can represent the set of all ordered pairs of the real numbers R2. So if you're in R2, let me get my black pen activated, then you can represent every point in R2 as an ordered pair sorry, some ordered pair. Okay, I'll leave it alone like that. So therefore, if it's a vector space, then the vectors in R2 could be V, okay, and this vector would be represented as some V1, V2, okay? And for any V1, V2, that will define all of the space R2, okay? So vectors in the space R2 always have that form, where V1 can take on any value, any real number value, and V2 can take on any real value. Say again? I know, it's just that statement. That is a vector space. Now what they should have done is shown that for any two vectors in the space, say V and U, where U would be, and by the way, I did what the book did and put parentheses there. Angle brackets I like better, but U1, since I started this one, parentheses, I'll end it with it. U2. Okay, here are the things that make that a vector space. Number one, if you add those two vectors together, you get U1 plus V1, U2 plus V2. That's in that space. So it's closed under vector addition. Number two, it doesn't matter the order you did. In fact, I just said it in reversed order. V1 plus U1, comma, V2 plus U2 is the same as U1 plus V1, comma, U2 plus V2. The order doesn't matter. Okay? So that shows. If you had a third vector there, how you group them together to add. As long as the third vector is also in this space, two components, it doesn't matter how you piece them together, you're going to come up with the same thing. So associative property of addition holds. There is a zero vector, 0, 0, such that for every U in that vector space, R2, 0 plus that U is going to be that U. Okay? That's the fourth property. And then the fifth one, for every U in V, there is a vector minus U that's also in V. Minus U1 minus U2. And if you were to add those together, you get the zero vector. Okay? Those are the first 5, the addition rules. The multiplication rules is basically if you multiply a vector v, say, by some constant c, then you get cv1 comma cv2. That's also in R2. So it's closed under scalar multiplication. And if you take the sum of those two vectors, multiply it by a constant, so that's the same as the constant times the first plus the constant times the second. Okay, distributive property. Or if you had two constants, c and d, add those together times v1 would be the same as cv1 plus dv1. Cv plus dv. Another form of distributive property. And then that same c and d, or any old c and d, scalars, cd times v is the same as c times dv, which is the same as d times cv. They're all the same. Okay? And then finally, if you multiply 1 by that vector v, you're going to get that vector v. So all the proofs, all the things work. Now, I went through all 10, but in reality, basically, if you can show 1 and 6, in that definition, that's not quite fair. You got most of them covered. The only thing is that zero vector sometimes really throws things off. So that one's pretty weak. So is example 2. The set of all ordered n-tuples of real numbers in Rn. Now we're not just doing 3 space, any n space, where n is some integer. 17, 45, height. No, that's okay. Yeah, okay. Any n-tuple of real numbers, with the standard operations, is a vector space. Okay? Theorem 4.2, which we where is theorem 4.2? I guess it was back in the previous section. I was sure not in this one.
You would think it'd be in this section.
You would think, but I guess they don't do 4.2.1.
It's the same one that starts off for the section.
Yeah.
This big box. It's just
Yeah, but it's Rn. Yeah. And this definition is for vector spaces Rn where the properties. Those properties met, you have a vector space. So, vectors in that space are in the form of V is V1, V2, V3, up to Vn. Okay. Now, the next 3 examples describe vector spaces in which the...
These are all like proofs.
Lost it. Okay, there it is. Does not consist of ordered n-tuples.
These are all like proofs. There's no specific example. These are all very general
Right.
examples.
Yeah, exactly. Each example describes a set V and defines the 2 vector operations. The standard vector operations are your vector addition and scalar multiplication. That's it. With those 2 operations. Now, they don't have to be your standard ones. You could define others, but we'll take it. So, here's one that's not an R superscript anything. Vector space of all 2 by 3 matrices. Okay? So this time we'll do I thought they were going to choose A. Now, it's called a vector space, so technically these are vectors, but they're not vectors as we have been naming vectors. They are actually matrices, as we have normally named matrices. And this would be 2 by 3, so that's going to be A11, A12, A13, A21, A22, A23. Okay? Now for any 2 by 2 matrices, under the standard rules of things, if you add those two together, that is also a 2 by 3 matrix. Yes, it is. If you multiply that matrix by a constant C, you get a 2 by 3 matrix. Yes, you do. So the standard rules for matrix addition, which in this case is a vector addition, and scalar multiplication of the matrix, which is scalar multiplication of that vector that we're defining this way, they work. So, now, obviously 1 and 6 are done because those were the conditions we said they have to meet. But if you take any two 2 by 3 matrices, add them in either order, you get a 2 by 3 matrices and the same one. Okay? So number 2 is met. Number 3, if you had 3 of those 2 by 3 matrices and add them any way you want to add them, okay, you're going to get the same answer. Okay? So the associative property is met. There is a 0 matrix, 2 by 3 matrix, and that would be 0, 0, 0, first row, 0, 0, 0, second row. When you add that to A, you're going to get A. Okay? So yes, there is a 0 vector. Okay? Matrix. Okay. And for every one of these, A in this 2 by 3, there's another one, namely minus A1, minus A2, minus A13, minus A21, minus A22, minus A23, that when you add them together, you're going to get the 0 matrix in this space. And sure enough, I just named it. Scalar multiplication, 6 was defined just as we did. And then if you took any two, you're going somewhere warmer. Okay. Good luck with that. Okay. It's probably warmer outside, isn't it? Because it was already.
Oh, yeah.
Okay, you can open them if you want to. Make us all feel a little better. Okay. You can go through each one of those. C times A plus B would be CA plus CB. I mean, B. CB, huh?
I'm just sitting at the desk, but at least I'm getting more air.
Yeah. If you had two scalars, A plus B times, let's call it C plus D times this matrix A, that would be either C times A plus D times A, or C plus D times A. Same thing. So that works. And then the order in which you multiply it, as long as they're scalars, C times DA is the same as CD times A. Know that one. And if you multiply this matrix by the number 1, you get this matrix. So all those are met, so that is indeed a vector space. Okay? So guess what? We've now defined vectors to be things other than what we think of as directed line segments, or column vectors or row vectors. They can be a matrix, as long as it's all the same size matrices. Okay.
And
now,
that matrix defines a vector?
Yeah. Okay.
A single vector?
What we were calling matrix A, we can now call vector A, and other matrices that are, now these are all 2 by 3s, by the way. They have to be 2 by 3s for that to work. Or they all have to be 3 by 2s, or 7 by 7s, or 8 by 3s, or whatever. Yeah.
I would just have to see that I would have to see a vector you plugged into that, because I would think one row would be a vector.
I know, that's what I'm saying. We have now, in the terms of vector spaces, this is a vector because those matrices follow the same rules that vectors follow. So therefore, we can consider this, in some sense, a vector. Okay. So expand your concept of vectors.
It's not just lines.
What's that?
Not just lines.
Not just lines anymore, or directed line segments or anything. They have now taken on new meanings. Now, if that wasn't weird enough, the vector space of all polynomials of degree 2 or less is a vector space. Okay? And we're going to name that P2. That means the set of all polynomials of degree 2 or less. That would include the zero polynomial, just the number 0, every constant polynomial, 17 minus 4/3 pi, whatever, any linear polynomial, a plus 2b, b, ax plus b, or whatever, any linear polynomial, and any quadratic polynomial. The set of all polynomials of degree 2 or less, so that would be represented by p of x is equal to, now, yeah, they write them the same way, a sub 2 x squared plus a sub 1 x plus a sub 0. Okay? Now, not following the rule that we said for quadratics. Okay? Quadratics, we require the a2 not be 0. But when you're all polynomials degree 2 or less, that allows a2 to be 0. Always a1 and a0 could be 0, but now any of them could be 0. Even all three of them could be 0. You have to have that because you have to have the 0 vector. The 0 vector here would be 0. Yeah, exactly. Just as the 0 vector up there would be 0, 0, 0, 0, 0, 0. Okay? In 2 rows, 3 columns. Okay? So this is not quadratic polynomials, but polynomials degree 2 or less. Okay? And then you step back through every one of the rules before. Add any two polynomials degree 2 or less together, you get a polynomial degree 2 or less. Okay? You can never jump it up to 3. Not by addition. Okay? Doesn't matter which way you add the polynomials. If you have this polynomial, you have another polynomial, add them in either way, you're going to get the same polynomial. Okay? You had 3 of them, add them any which way you do it, you're still going to get a polynomial in piece 2 space. Okay? There is a 0 polynomial, 0, that when you add it to any of these old polynomials, you'll get the same polynomial. And there's another polynomial, as in negative a2 x squared, negative a1 x minus a, that when you add them to this one, you're going to get the 0 polynomial. Those are the 5 addition rules, the multiplication rules. Multiply this by any constant, you get a polynomial in P2. Even 0, okay? It'll still be in P2. Negative, huge numbers, small numbers, it doesn't matter, you'll still be in P2. Then the distributive rules, that if you do C times P of X, it's in P2, plus Q of X in P2, still say that would be B2x squared plus B1x plus B0. Add those together, multiply C times the sum, and it's the same as C times 1 plus C times M. Okay. It's pretty straightforward. Every one of those will work. Okay? So that now, polynomials can be a vector. Really strange. Okay? Matrices, certain matrices are vectors. Polynomials can be vectors. Huh? Yeah. Because they belong to a vector space. Okay? Now. Okay. P sub n is defined as the set of all polynomials of degree n or less, together with the 0 polynomial, which of course that's the degree n or less. Now, actually, if you go back to when they were defining polynomials, that is a strange thing that sometimes some books would say a constant polynomial would be y is equal to c. But then some books will say as long as c is not equal to 0. Well, it's still a constant polynomial with c equals 0. It's just that not up here, not down there, it's 0. But some books hesitated to call that a polynomial, okay? Now you have to. I mean, otherwise you don't have a 0 vector, and it doesn't fulfill all the rules, okay?
Yeah, I don't know why. That's kind of odd.
It really is, and I've never quite seen the reason for it, but they tend to do that. This one makes a special point of saying together with the 0 polynomial. So it is a polynomial, but make sure you don't leave it out. The procedure used to verify that P2 is a vector space can be extended to Pn, that just means polynomial degree n or less. Now, let's look at example 5. I don't think this is going to take more room, but just in case it does, we will. So let's C now be a set of all real valued continuous functions, okay? Previously, P was polynomial functions. Now C is going to be real valued continuous functions. Now, all polynomial functions are continuous functions. Can you name me any non-polynomial functions that are continuous functions? R. I know you can. I know you can, but you may not realize you can. How about this?
Q,
Sine, cosine. Tangent, cotangent, no. Secant and cosecant, no. But sine and cosine, yes. What did you say?
It's cubed, but it's an x
The
cubed.
cubic function is a polynomial function, right? Okay, but now exponential functions are continuous functions, not polynomial.
A log.
The log function over a certain interval is
Somewhat.
a continuous function. It's not over minus infinity to infinity. Okay. So it would fall under this classification. But the others we named, and there are others as well. But let's this be a set of all real valued continuous functions. So square root could not be. Square root doesn't go to minus.
It stops
At 0. It starts at 0 and goes to infinity. So that wouldn't be here. Cube root would be. 5th root, 7th root, any of those roots would be.
You could be like x to the n, or x to the 2 plus n.
X to 2 plus n.
So
Yeah, that's an exponential function.
or
Exactly.
x to the minus 2 minus n as well.
Okay.
Well, not minus 2, be 1 over 2.
Okay.
Square root.
Right. Okay. I think I got what you're saying.
Basically, continuing every root after square root of 2. It has to be above square root of 2.
Well, those 4th roots don't work either. Wait, no.
It'd be even root, or odd roots.
Odd roots, yeah, right. Okay. Now, I don't know if this was included in what you were saying, but a negative exponent wouldn't work
Would not.
because anything that would be 0 in that denominator, that would throw it out of this domain. Okay. It would be defined everywhere except 0, and that wouldn't be continuous at 0. So, there are a few that wouldn't be, okay. In fact, probably quite a few that wouldn't be. Okay. But all those that are, and there are quite a few of those too, set of all real valued continuous functions defined on the entire number line. That set consists of all polynomial functions, of course, and all other continuous functions on the entire real line. For example, sine x, e to the x are members of that set. Now, addition is defined just as we did before, that f plus g of x is equal to f of x plus g of x, just like before, and that c f of x is equal to c times f of x. Scalar multiplier, okay? Certainly works for every x on from minus infinity to infinity, show that that's a vector space. Okay? You'd have to go back to all 10 of those. Basically, the first and the sixth one are basically defined by these things here. Not quite. I mean, it just shows that these are all in that vector space. They all qualify. The order at which you add functions doesn't matter, so that, and the arrangement in which you add functions doesn't matter. So 2 and 3 are covered. There is a zero function that when you add it to f, you get f, and that would just be g of x equals 0. Okay? So that fits. And that there's for every f, there's a f of x, there's a minus f of x. When you add those two together, you get the zero function. Okay. Scalar multiplication, basically we use that in there, and that's still in the set. And then your distributive laws, if you had a C plus D, you know, all that, or a C times F plus G, you know, that works too. Okay. And 1 times F is F. Okay. All pretty straightforward. Okay. And basically, other things that we were talking about, when you add continuous functions, you get continuous functions. You know, you can't add two continuous functions together and somehow introduce a discontinuity. It just doesn't happen. Dividing, it could. Okay, but that's not part of it. So here is a summary of your important vector spaces. R, it's the real number line. Okay? R squared, plane. R cubed, space. R sub n, it's not sub n, superscript n, super n. That's the set of all, sorry, n tuplets. C, this one right here, defined from minus infinity to infinity, set of all continuous functions defined on the real number line. And then there's another C listed here. Okay. So, yes, on a closed interval A to B. Set of all continuous functions defined on a closed interval A to B. Okay? Now, the key here is defined on that. It's not where they end up, but it's defined on A to B. And that works also. You can go back and check them point by point. Okay? Now, when they just say P, that's the set of all polynomials, period. Or P sub n is all polynomials of degree n or less. Okay? And then you had M, let me get it right, M n, that's the set of all matrices that are m by n matrices. They all have to be the same size, which a subset of that is n by n. Okay? Set of all square matrices. Second? Oh, go back. Figure out what you were telling me. Okay. So the set of all n by n square matrices. Now, are they all? Well, probably not, but they're all the ones we'll be messing with. Okay? Now, I love their next little sentence here. You have seen the versatility of the concept of a vector space. Yeah, right. Okay. No, I hope you have. Sort of. Okay. For instance, a vector can be a real number, an n-tuple. Okay. You have seen the versatility. Okay. Yeah. I focused on the wrong word there.
You see the versatility of the concept.
Of the concept of the vector space, that that now defines a vector to be all kinds of things. Okay, it could be a real number, an n-tuple, plane, line, space.
It's like the German word bitte.
The what?
The German word bitte.
Bitte?
It means like it's like thanks. I'm sorry. It's all sorts of.
Oh, I see. I didn't know that. I thought it was.
Maybe pronouncing it wrong.
Yeah. But matrices, polynomials, continuous functions, so on and on and on and on. But what is the purpose of that abstraction, and why bother to define it? It's the more important questions there. There are several reasons, but the most important reason applies to efficiency. The abstraction turns out to be mathematically efficient because the general results that apply to all vector spaces can now be derived. Once, a theorem has been proved for an abstract vector space, you need not give a separate proof for n-tuples, matrices, and polynomials. If it's a vector space, it fits. Okay? So, here's a theorem. Enough blah, blah, blah. Again, it seems like today is just filled with this, both courses. Let V be any element of a vector space, capital V. So let vector V be any element of capital V vector space. Okay? And C be any scalar. Okay? Then these things are true. Seems like we've seen them all before. The number 0 times the vector V that's in that vector space is going to be the 0 vector. Okay?
Might as well just be 0.
No. What's that?
It might as well be the number 0 because they're about the same thing.
Right. And C times the 0 vector, guess what? Is going to be the 0 vector. Really creative here, aren't they? In fact, all but the last one have zeros in them, okay? Here's another, and this is, okay. If C times V is equal to the 0 vector, okay, then what might be the ramifications? Either C is equal to 0, the number 0, or V is equal to the 0 vector. Okay? Absolutely right. And then finally 4. Only one without 0 in it. -1 times V is equal to -V. How creative. Okay. And surprising. I never would have expected that to be the case, right?
That's earth-shattering information.
You got it. Okay. Now, to prove those properties, you're restricted to using the 10 vector space axioms. So you almost have not quite 10 things to do to prove each one of them, so it's, to me, really gets at least tedious and sometimes just totally monotonous and boring. So much so you almost forget, what am I showing here? It's so obvious. Why am I trying to write this, but so that happens. Now, there is a blurb, excuse me. There is a blurb at the bottom of the page, another linear algebra applied. Goodness gracious, this is so hard to breathe. You're talking about degrees of freedom. Now, this example is sometimes the term degrees of freedom and what they're meaning by degrees of freedom and what is commonly known as degrees of freedom may be a little bit of contradictory or incongruous or something like that.
Makes me think of the temperature in Fahrenheit.
How's that?
Degrees of freedom.
Yeah, well, okay.
Because
Degrees Fahrenheit.
the U.S.
Yeah, okay.
One of the few countries uses it.
Their example here shows masses on springs, okay? And they're talking about the differential equations that solve those, okay? And basically, it was something I came awfully close to saying in the last class. I actually did sort of say it, but if you have a third degree, third order differential equation, you either are going to have 3 arbitrary constants, or you're going to have, you don't need any more than 3. When we're getting at the end there about linear independence and dependence, that was getting toward what I'm talking about now. Okay? And that's what they're saying here, is that basically is what they're saying. If you can describe this system with a second order differential equation, you've got to have 2 arbitrary constants that you either have to define or keep in the problem. Okay? If you have, you've got to have 2 either initial conditions or 1 initial, 1 boundary or something, 2 things that are met before you can determine what those conditions are. But when I see this, the masses on the springs here, and when I think degrees of freedom, this is where my mind is wandering off to. What if you start hitting them side to side? Now you're introducing all sorts of other degrees of freedom. As long as you're pulling downward and letting them spring up, you can describe that. But that's why I thought, surely there's got to be something else, a better illustration of this than springs, because I can visualize them going all over the place, and then you have way more degrees of freedom than what you really want to have there.
Maybe a pendulum.
Yeah, that might be true, except that unless you let the pendulum do this. But that would be...
If it was on just an elbow.
Yes, exactly. And you're restricted to that. I think that would be a better example. But that's a more complicated equation than what this one is. So I see why they're doing it. But that's why... Yes, exactly. This is... when I first looked at this, I went, oh no. But you see, the pendulum, you're really restricted to small angles, because when you get big angles, you start getting, it's kind of like spherical aberration on lenses. You know, there's no perfect lens if you let it be too large. You get too much destructive interference, you know. So yeah, it's another issue. But when I looked at this, I thought, oh, there's a part of me that doesn't like this example. But what they're trying to show was exactly right. All right, so let's look at some sets that are not vector spaces. Now, all
examples?
Yeah, sort of like counter examples. Okay, sets. Okay, all vector spaces are sets. Okay, you define them as sets, but not all sets are vector spaces. Okay.
Okay. Everything's a vector. Okay, not everything. Sort of.
Right. So here's what. The set of integers is not a vector space. Can you think of why? Set of all integers is not a vector space. And the problem is in the wording.
Set of
Okay?
all integers does not form
Right. When you do scalar multiplication, remember that we said where C and D are real numbers. Go back to page 155. your definition of vector space, before you start those 10 examples there, 10 conditions there, notice up there it says, where every scalar, real numbers C and D. Okay? Well, if you have an integer, any old integer, 17, multiply that by any real number, 0.5, not going to be an integer. So that's not closed under scalar multiplication, because by scalar we mean any real number. And certainly that's going to throw it outside the space, okay? Because we define the scalar to be any real number. Now, if you defined your scalar to be integers, you just can't. I mean, the requirement is that you multiply a vector by a scalar, you still get a vector, okay? That's any real number. It can't be restricted, okay? Now, the set of second-degree polynomials is not a vector space. Second-degree polynomials is not P2. Remember what P2 was?
Second order.
Or less.
Or less.
Yeah, but second-order polynomials wouldn't be, okay? Because number one, I mean, there's several reasons. You could have a, boy, I don't know what to name it. It's not P2, but let's just do a polynomial, second degree, okay. 2n squared plus 3n plus 1.
I think it's piece of n.
Piece of 2.
Or n.
Or n, okay, well, that relates to the variable.
Okay, that works.
Okay, but there's a second degree polynomial. Here's another second degree polynomial. Let's call it Q2. 2n squared plus 4n plus 7. Okay? Well, or even better, make it a minus. If you add those two together, you're not in a second degree polynomial anymore because those went out. And the very first thing said addition must be closed. So if you add two polynomials of second degree polynomials together, any two, it has to be a second degree polynomial. That one wouldn't be. That would be a first degree polynomial. As you do second degree polynomial or less, no sweat. Okay? But not to second degree. Okay? I was going to try to give another one, but that might be more confusing, so let's leave it alone. Another set that's not a vector space. Now this one starts off sounding like it would be, okay? Let V, this vector space, equal R2. Now we've already said that's a vector space, okay? The set of all ordered pairs of real numbers with the standard operation of addition but non-standard definition of scalar multiplication. So the standard operation of addition, that would be that for any ordered pair in this space, U equal U1, V, U1, U2, and V equal ordered pair V1, V2, okay? You add those together, you get that, so U plus V is U1 plus V1, comma, I'm putting parentheses again, this book is getting to me, U2 plus V2, okay? And that's in the space, so that's no problem. That's our standard definition for that. And our standard definition for scalar multiplication was C times U is equal to CU, okay? Okay. But now we're going to use another definition of scalar multiplication, not this one, because that one would be C times U1, U2 would be C U1, C U2. Okay? That's the standard definition. This non-standard definition is that C, I'm going to stay with what I did. They did X, but I'm going to do U. U1, U2 is equal to CU1, 0. Okay? Now, it says show that's not a vector space. Well, technically how you do it was go through every one of these, okay? Well, any U1 plus U2 is still going to be a vector space. Doesn't matter the order, that would be a vector space. In fact, all your additions still work okay, okay? So when you get into your multiplication ones, that's where you're going to run into problems, okay? Specifically, that very last one. 1 times U1, U2, what's that equal to? U1, 0. And that is not equal to U. U is U1, U2. So the requirement is that 1 times U equals U, but we see here that 1 times U is equal to something not U. Now that may not be the only one, but that to me is the easiest one to show. Okay? So does that mean you can't come up with other definitions for your addition or multiplication? No, you can. But not all standard, non-standard ones will produce vector spaces. Some might, but not all of them will. This one certainly would not. Okay? Now they gave...
You got me kidding me.
What?
This is the last example for the section.
What's that?
This is just a very generalized section.
It really is.
I'm hoping we're going to use this in the next section, right?
Yeah. We're going to be talking about vector spaces the entire rest of the chapter and beyond. But, so...
It's just, this is like, this summary of important vector spaces, it's like...
Yeah.
I feel like it's just 2 tables that are explained and broken down.
Exactly. That's pretty much what it is. A few examples and a few counterexamples. That's it. So, try doing any of the odds 1 through 5, any of the odds 7 through 11, odds 13 to 33. There's a whole passel of them there. Do some of those, okay? Try doing 35, okay? And 37's a proof. You could try that if you'd like. I think it wouldn't be too bad, except providing full detail. Okay, that sounds ominous. 39 I don't think would be too awfully bad. And then 41 is sort of like that application problem. So our applied problem, linear algebra applied. And then you can look at 43 as well. Okay. Now 45 is a true false. Good idea to read through that and figure out whether they're true or false and find out why they're false if they are. Okay. 47 is another proof that you certainly are welcome to attempt if you'd like.
Can we do 45?
Let's try.
Because it kind of reminds me of the prelim.
Okay.
Questions.
All right, let's try it. Okay, true or false. In these exercises, determine whether each statement is true or false. If a statement is true, give a reason or cite an appropriate statement from the text. If it's false, provide an example that shows the statement is not true in all cases, or cite an appropriate statement from the text. Okay. So 45 is that the one you want to do?
Yeah.
Okay. 3 parts. A vector space consists of 4 entities: a set of vectors, a set of scalars, and 2 operations.
Well, let's see. Set of vectors, that'd be a yes, right? That makes sense.
Yeah.
A set of scalars also makes sense.
Yeah.
2 operations, we have adding and multiplying.
Yeah. And basically,
I think that's it.
in a sense, that unless there's some bizarre thing they're thinking that I'm not thinking, that should be it. So sure enough, A is true. Okay? B, the set of all integers with the standard operations is a vector space.
Set of all integers with standard operations. We said that was a no.
That was a no, and we could go back and show that.
Because it's right there.
Yes, exactly.
It could be the 1 times whatever does not equal U.
Well, 1 would be fine. It's C. This is the one that falls. Because remember, C is required to be any real number. You multiply a real number by an integer, and unless that real number happened to have been an integer, or the real number was a perfect fraction of that integer, yeah, it's not going to work. But pi times an integer is never going to be an integer, okay, for instance. Okay. All right, so that was false, but it was shown to be. C, the set of all ordered triplets, x, y, z, of real numbers, where y is greater than or equal to 0, with the standard operations on R3, is a vector space.
Set all ordered triplets, real numbers, where y is greater than or equal to 0. Okay, so basically it's saying the y part of it's 0 or bigger.
Yeah.
So x and z can still be anything. I don't see why it wouldn't be.
Okay. Give me a C.
1.
Okay. How about negative 1? Okay. Then is C times xyz in xyz? That'd be negative x. Yep, that's there. Negative z. Yeah, that's there. Negative y is not there.
Yeah.
So, yeah, it's not closed under. Yeah. So that, I think, has to be a false. Let me make sure. What says 4, 2, 45. False with the standard operation of R3. Additive inverse axiom is not satisfied. Well, there's another. I said closure on this scalar multiplication was not satisfied.
Yeah, because you couldn't have a negative y.
You could not have a negative y. If you had a y, you can't have a negative y to add to it and get a 0 vector. Right. So, good deal. Glad you said that. That was worth an exercise. Now, that was vector spaces. How are we doing on time?
It is 12:01, so we got 14 minutes.
14 minutes. So let's get started in 14.3. We've been talking about vector spaces. So now we're going to do subspaces of vector spaces. Now,
Like the garage.
kinda, okay?
The basement of vector space.
Yes. Yeah, those below ground. Okay, subspaces. Okay, I got it. Okay. Sick mind. Okay.
I can think of at least.
Okay. The I think the idea is, I'm not sure, but this is how I frame it. Somewhere back in math, you probably studied sets, right? Back when I was young, we didn't, but at some point we ran into sets.
What do you mean sets?
A set of numbers.
Like 1, 3, 7, 5.
Yeah, right. Yeah, sets of numbers, and then you said subsets of that set. Okay, that would be every element in the subset must be in the original set or else it's not. So if you had 1, 3, 5, 7, 9, in other words, your odd integers, 2 would not, 2, 3, 5, 7, 9 would not be a subset of that because 2's not in that set. But 5, 7, 9 would be in that set. That would be a subset. Okay. Now, we've been talking about what vector spaces are. Now, to be a subspace, it certainly has to be a because a space, a vector space is a set, okay, with those requirements. But not any subset of that set will necessarily be a vector space. That will be a subspace, I'm sorry. And that's what we're going to get at here. In many applications in linear algebra, vector spaces occur as subspaces of larger spaces. So it's sort of like some other room in your house, okay? Here would be, since you brought up the house analogy, this isn't bad, okay? Let's say your house has certain requirements to be a house. And literally today, I think pretty much these are true. Well, let's make a few of those requirements. It has to be on a good foundation. It has to have running water. It has to have sewage system. It has to have some type of ventilation. It has to have some sort of ingress and exit. Yeah, you can make up these rules that are going to be a house. Okay. Now you said some room in the house, like the basement. Okay. It has to have a good foundation. Many of those things may be, but it may be the basement doesn't have running water. If it doesn't have a bathroom or a kitchen, more than likely it won't have running water. So even though the basement is a subset of the house, for sure it's part of the house. It may not be a subspace of the house if that's how you define the space of a house.
It would, okay, or even a better example would be the shed.
Yeah.
Yeah, that might be a subset, but it would not be a subspace because it probably wouldn't have ventilation, a good foundation, or anything. It may just be a wooden shack in the house.
Yeah, but if it was not part of the house, it may not even be a subset of the house. Okay, even so, I don't know. Yeah, but that
On
is
the property.
very good on the property. Okay, or the farm. Okay, right. Okay, okay.
Let's just not buy it.
Right. So in many applications of linear algebra, vector spaces occur as subspaces of larger spaces. For instance, you'll see that the solution set of a homogeneous system, boy, we can't get away from this in either course, can we? Of linear equations of n variables is a subspace of Rn, okay? And that's coming up later, okay, Theorem 416. A non-empty subset of a vector space, now a subset of a vector space is a subspace when it is a vector space with the same, remember, 10 operations we had to have before, same operations that defined in the original vector space. So it has to be a subset of the same set, but it also must be a vector space on its own right and meet all the requirements. Okay? So here's your definition of a subspace as a vector space. And actually, you don't have a book, so I'll write this down. I don't think Javon has the same book anyway. So here's the definition of a subspace of a vector space. A non-empty, so wait, that's probably too confusing. Okay, let me write it out. I thought I would use a symbol there, but you might not be familiar with the symbols, and I'm not sure I would have it right anyway. A non-empty, because technically, by the way, folks, an empty set is always a subset of any set. Okay, in sets, empty set is a subset of any set. Okay, so
because it contains nothing, so it can't.
Yeah,
it contains nothing the other set doesn't have.
Exactly right. Okay. because it contains nothing. Yeah. Okay. But now we're restricting, we can't have an empty set being a subspace. So it has to be a non-empty subset W. And here I really do want to use it. You should be at least a little bit familiar with these notations, okay? I sure hope I remember them right. That's a subset of. Do y'all remember that?
Just a C.
It looks like a C. It just doesn't curve at all. It's just, curve down at all. That's a subset, a non-empty subset W. They spelled it out. I'm just lazy. Of a vector space V is called a subspace Okay, so it has to be a subset, but not an empty subset of the vector space. But not only that, it's to be a subspace of V when W, the subset, is also a vector space in its own right. Okay, in other under the rules of addition, that's technically vector addition, and scalar multiplication defined in V. Now, this is the part to me that can be a little squirrely, so I'm trying to warn you not to let it get squirrely. Okay. V is a vector space. Okay. W is some subspace of that, but it has to have elements in it. It can't be empty. Okay. Now, W is a subset of V, but it's not necessarily a subspace, but it is a subspace when it's a vector space in its own right, but it has to be using the same operations of vector addition, scalar multiplication that were defined for V. Now remember, we have our standards, but then you could have others. Yeah, we'll let this be that. But whatever you assume for V, it's going to have to work for W as well.
Okay. So they both have to follow those 10 rules.
Yes.
So they can both be vector spaces.
Right.
And anything that's going on in V specifically kind of has to be going on in W as well.
Yes, it has to be going on in the same manner in W. Okay. And follow all 10 rules. Okay. W could be a subset, but not. For instance, here's just a really dumb example. Remember, for V to be a subspace, it has to contain the zero vector. Okay?
For it to be a vector space.
Vector space, yeah, it's a vector space. Okay? Now, W can be a subset of V without having the zero vector, but then it could be a subspace because it has to have to be. So that's one really obvious one. Okay. Okay.
So they both always have to contain the zero vector.
Yes, exactly. To be a space or a subspace, vector space or a subspace, you have to have a zero vector defined.
Okay.
Okay.
That kind of narrows it down.
Yeah. Okay. So here's a subspace of R3. Okay. I think I can fit it on here. Let's try. Show that W, which is equal to the set of all ordered triplets, x1, 0, x3, such that x1 and x3 are real numbers. Okay? That's your subset of space. X, Y, Z. Okay? Or x1, x2, x3. Certainly it's a subset. Okay? Is it also a subspace? Okay? And we're using the standard operations just like we did before. Okay? Now, you'd have to go through and say, for any two vectors in this, say x and y, where x would be x1, 0, x3, and y would be y1, 0, x, y3, okay? When you add them together, you still get a x1 plus y1, 0, x3 plus y3. So that would be in the space, okay? It's closed, okay? Order, wouldn't matter how you added them. If you had a third one, z1, 0, z3, add those in any order, it still works. I mean, go through every one of them, okay? Again, go back to that first one. Go through all 5 of the first thing. Oh, there is a 0 vector because remember, x1 and x3, they have any real number. 0 is a real number, 0 is a real number, so that contains a 0 vector. Okay? You have minus x1 and minus x3, minus x1, 0, minus x3. They add to be the 0 vector. So those all fit. Any constant, real number constant, multiply that, is still going to be something, 0, something. So that's closed. And any two of them added together, it's going to be, and any two constants added together. So yeah, and 1 times this is that. All 10 of those meet. Okay? Now, what are we talking about there? X-axis, y-axis, z-axis. Let's talk about the XZ plane here. XZ plane is a vector space. Okay? As a 0, everything fits. Okay? So sure enough, that is a vector space. This is a subspace of V. It's a subset of V, but it's not a sub. But it's also a subspace of V. Now, the y is equal to 1 plane. 1 unit off of that. That is also a subset, but not a subspace because it doesn't have a 0 vector. You got it. Yeah, and we're out of time. Okay. So we'll say that we did example 1. We'll start next time with theorem 4.5. Made pretty good progress today, I think.
Yeah, we killed
Huh?
section. We got to a section.
Yeah. So let's close this.